Okay, so the material we were working on last day, we did the up and down, the translations, up, down, left, right. So what we're looking at today is the reflections and stretches. So basically, when you take your graph and you add something to it and you make it go wider or you go narrower, those, they call them reflections and compressions or stretches. So in A, if you compare the graph of y is equal to fx to y is equal to f of negative x, so we're putting in a negative sign in there. That's all we're doing right now, is just doing that sign switch. So if you do on your graphing calculators y is equal to square root x, your graph is going to look something like that. Y is equal to square root x. This one. So if you do y is equal to the square root of negative x, it's just going to do this to your graph. So what happened when x is replaced by negative x? It flipped it over, right? The y-axis. So when that negative sign is applied inside your function, then you get a flip over the y-axis. No, it's half of a parabola. So in the second one, we're still doing our base graph of y is equal to square root x. So that will look just like this. Oops, pretend that went through there. When you do apply the negative, so it's in front of the y. So instead of making the x values negative, you change the y values to be negative, then your graph is going to have a different look to it. Remember, when you're doing them on your graphing calculator, we can't enter in this negative like this. So we have to solve the equation for y. So if we're starting at this, to get rid of that negative, you're either going to multiply or divide by negative 1. Oops, that should be a negative 1. So we'll have y is equal to negative square root x. So that's what you would enter in your calculator. Y is equal to, you have the y is equal to is there, and then the negative sign is on the outside, then your square root x. So this graph does that. Right. In the first graph, the negative was inside that square root sign, and in the second one, it's in front of it. Okay, that's why I said do these in your calculator afterwards. We'll try one, and then you can do the rest later. So what happens to our graph when we replaced y with a negative y? Where did it flip? It flips over the x-axis. Yeah, should be a 1 there. Nope. Okay, so C, instead of just putting a negative in there inside that bracket, what happens if we actually multiply something to our x values? So our basic graph, y is equal to x squared, is just that parabola. So I did. Y is equal to 2x squared. When you, it's going to be a parabola if it's squared, right? When you put this in your calculator, you'll see that it goes skinnier or narrow. And this value here is at 1/2. And then this value here is at negative 1/2. Right. Right. The bigger that value is, yeah, the narrower your graph is going to be. We call it a B in here. Okay? So it says what happens when we replace the x with a 2x. Well, it does what we call a horizontal compression. Okay? So that graph was squeezed together, made skinnier by a factor of 1/2. And you can look at it and see that it's half as wide as our original graph. Yeah, you could put, they kind of answered it in that right here. So then it says we can obtain the coordinates of each image point using this factor. So using that 1/2 factor, you can find out what all the other points would be on this graph by using that 1/2. So it says, for example, the point 2, 4 on the y x squared graph, so 2, 4, which would be up here, has changed to 1, 4 on this compressed graph. So 2, 4, say it's about there, and on this graph it would be right there. So all we've done is taken this 1/2 and applied it to that. Right, so what you end up doing actually is you're multiplying. Whatever this factor is, you multiply it to your x values. Mm-hmm. Yeah. So this one here, if we take these coordinates they gave us and try to find their images on that y is equal to 2x squared graph, then we're going to take each one of the x coordinates and either think of it as multiplying by 1/2 or divide by 2. It's the same thing. Just the x will. And that's because this value is inside being applied to that. So 2, 4 then would change to 1, 4. Negative 1, 1 will change to negative 1/2, 1. And negative 2, 4 will change to negative 1, 4. So all we did is we took every x value and we have multiplied it by 1/2. Because multiplying by 1/2 is the same as dividing by 2. So then it says what happens horizontally to the function when x is replaced by kx and k is greater than 1. Okay, so instead of having just an x in there, if we substitute a value in there and that value is greater than 1, then what actually happened to the graph? It got smaller and it changed by a factor of, well, yeah, narrower, better word. Changed by a factor of 1 over k. This was a 2 in here, so our factor ended up being 1/2. If this had been a 6 in here, then it would be 1/6. Okay, so when the value is being multiplied inside, then that means you're going to, the factor that you're going to be using will be a reciprocal of it. So if we do y is equal to x squared and compare it to y is equal to 1/2 x squared, so it's less than a value of 1, what happens to our graph? So our original graph will be here, and then up at 2, 4. Whoops, that's more of a 2, 3. If it, yes. Yeah, if this is a 1, it's just our normal graph. If it was a number bigger than 1, it got narrower. And now this is a fraction, and if you remember from parabolas, when you had the fraction in front of there, then your graph got wider. So that's what happens to this one. So this one, instead of being at 1, 1, it's now at 2, 1. Right. And our next one would have been at 2, 4 on the regular graph. Well, now it's going to be at 4, 4. Yeah, origin's the same, because if you substitute a 0, you're still going to get a 0. Because we're doubling that x value, but the y value stays the same. Because normally, yeah, normally it would have been at 2, 4. On the blue graph, it would have been at 2, 4. But on the red graph, it would be at 4, 4. Right. Yeah. So it says what happens to our graph when x is replaced by 1/2 x? Wider. And we call that a horizontal stretch. So it's a compression when it was a 1 or greater than 1, because it squeezed it up, it compressed it, and it's a stretch or an expansion because now we're making it wider, we're squishing it out. And it's a horizontal stretch by 2. We doubled those x values. No, because only the x value is being affected by that. No. Because this stuff is recap. Well, you just need to know what are the effects of those values on your graph so that you don't have to do a t-chart every time. Okay, so this says comparing y is equal to fx to ay is equal to fx. So now this value here, that a value, is being applied to the y. In the last example, it was being applied to the x. So if we do an absolute value graph, if you remember the absolute value graph makes the v, so then this would just be at 1, 1, 2, 2, 3, 3, 4, 4, and 0, 0, of course. When you're doing these for real, you should use a straight edge for things like this. The second one? Yes, we do. So in this second equation, we have 2y is equal to x. Well, you can't do 2y is equal to x on your calculator, and it's easier to do if you stick that, or keep the y by itself. So if we start with 2y is equal to absolute value of x, then we divide by 2. Well, because in your calculator, it's easier to put 1/2 and then absolute value x. What do you mean, can you move it back? Well, you could, but here? Yeah. Yeah, it doesn't matter where you put it. You just have to remember that it's there. Well, because if you divide by 2, it's the same as multiplying by 1/2. But you can't, and if you have to be really careful when you put that in your calculator, where you have to put your absolute value signs there. And then put the divide by 2. Because if you don't close off that bracket, it's going to do absolute value of x over 2. And that's not the same thing. So this graph here then, when you go to draw this, it affects the same way as it did with the squared graph. Oops, I missed that one. So now instead of being on every one of the y values, like it was here, it went 1, 2, 3, 4, it's at a half, 1, 1.5, 2, and then it'd be at 2.5, 3, and so on. It isn't. No, what's throwing you off is there's that f in front of there instead. Because that is the same. That in that first example, it said this. Or this is the same as saying. Well, then I'm not sure. You'll have to show me. No, because it doesn't affect the y value when it's inside here. Mm-mm. Nope. Because remember, you always went. So on this one, we would have done the 1a, 2a. Remember when we did our steps? 1a, 2a, 3a. So if this is a 2, you go 2 times. This would be over 2. This would be a 4. This would be a 3. You still went over 1, up 1. Or this time you go, sorry, over 2, up 1. This time is over 4. Okay? But you're still going only up that one amount, not doubling that amount. Okay. This means the same as that. Divide by 2, multiply 1/2. Same thing. Yeah. Okay, so it says in number 3 here, we can see, we can say that there's been a vertical compression by a factor of 1/2 to the function y is equal to square root of x. And what you're going to find out is they interchange the words. A horizontal compression is the same as a vertical expansion, and a horizontal, what was the word we used last time? They interchange them always. A horizontal stretch is the same as a vertical compression. So it's by a factor of 1/2 to this function. So it says you can obtain the image of each of those points using that factor, so using that 1/2. So it says, for example, 4, 4 on y is equal to x will change to 4, 2. So in the first example there, we divided our x value. This one, because our value was initially, was initially applying to the y, then we have to do that factor on the y. So you can take all of these coordinates now, these 1, 1, 2, 2, negative 1, 1, negative 2, 2, and find out what they would be on this graph by using that 1/2. So you're going to take your y values and multiply them by 1/2 or divide them by 2, whichever. So this one goes, if it was a 1, 1, it's going to be 1/2. 2, 2 is going to be 2, 1. So all I'm doing is dividing each of these by 2. Negative 1. Well, you have to remember what value is that factor being applied to, the x or the y value. Because if you look on your graph, this one was at 0, 0. This was at 1, 1. On my compressed one, I was still at 1 on the x. I just went to a 1/2 on the y. And then I went over to the 2 on the x, which is still the same as it was in the first graph. So my x's didn't change. The x coordinate, my y coordinate did. Well, vertical compression means that they've gone from an up down and are squishing it down. So it says what happens vertically, so up down wise, you compressed it. You're squishing this, and this is what they mean. The vertical compression is, so they've started here and it's like they pushed down on this, so it's causing your arms to flatten out. Okay, that's where the vertical compression comes in. You're going on the vertical axis, which is the y, you're pressing it down, causing it to flatten out. So what happened when we... Mm-hmm. Well, they're shortening and flattening, if you want to think of it that way. No? So this has a change when it is less than 1, when your k value or whatever the value is you're multiplying onto that y, it's changing it by a factor of 1 over a. So our a value here in our original equation was this 2y. This was our a. So we went 1 over a. Yep, it's an a. Yeah. Okay, next one. Same thing, absolute value graph. So your initial graph is just those 1, 1, 2, 2, 3, 3, and then on the negatives as well. Because we took our 2 from our equation. Our equation was 2y. So when we used it, we actually used it as a 1/2 value. Mm. In this one, your a value is whatever is being multiplied to the y. So in this one, my a value is a 1/2. So if I think of it, this is it will be. And if you go 1 over 1/2, that's the same as saying 1 divided by 1/2. So 1 multiplied by 2, so it's a 2. Okay? So if I look at this one, in order to solve for it, we need that y by itself. So if I'm multiplying by 1/2 to get rid of it, times by 2. So I multiply this side by 2. So I have y is equal to 2. No, same thing. I'll draw you a picture of a parabola later, and you can see it didn't do anything to the y's. It only did the x's. Okay. So now this one, this value of 2 is going to make everything move in. Right. Oops, I did that in the wrong one. No. No. That's okay. I'm on the right. Can't say I have one. Is it falling apart? Okay, so we have the graph for our y is equal to 2 absolute value of x, and as you can see, it's squished it up a little bit. That 2 has affected where we're putting the y values on there. So if we look at these, oops, move that out of the way. If we take the coordinates 1, 1, 2, 2, negative 1, 1, negative 2, 2, which are on that graph, and correspond the for the actual graph there of 1/2 y, Sorry, I'm just going to pause here for a second. Okay, sorry about that. So if we take those original coordinates, which would be from the y is equal to absolute value of x, and we find the corresponding coordinates for them on 1/2 y is equal to square root of x. We've said that our factor that they're going up or down by, in this case it's up by, is a 2. So we are going to take each one of the y coordinates and multiply them by 2 in order to get our expansion. So the first one would become 1, 2. Next one would be at 2, 4. The next one would be at -1, 2. And then the last one would be at -2 and 4. And if you flip back to the graph, that's where those, whoops, wrong one, down here at the bottom, that's where they were corresponding with. Okay? So we went 1, 2, and then halfway, because that was kind of a halfway mark, but 2 here and 4. So you can see how they've increased that y value by a scale of 2. So the question says, what happens vertically to the function when y is replaced by ky, and it's between 0 and 1, so it's a fractional value. It's an expansion. It's a vertical expansion, which, if you remember from the other stuff, was the same as a horizontal compression. So vertical expansion, horizontal compression mean the exact same things. Horizontal compression means you're going from the horizon, the x-axis, like this. This is the x-axis this way, and you're compressing it, so you're pushing it up that way. Vertical expansion means that if you take a look at what happens on the y-axis, you are pushing it so that it is getting closer. It's moving it this way. So it's making it closer and closer to that y-axis. So vertical expansion, making it skinnier and taller, and horizontal compression mean the same thing. So our reflection tools. So from the first examples there, when we had y is equal to f of -x, so that's when we added a negative value inside, we substituted a negative value to the x. What happened when we replaced the x with a -x? Well, we had a reflection in the y-axis, so it flipped on the y. And our coordinates were just a negative x value, and the y stayed the same. When we put that negative in front of the y, then we had a reflection in the x-axis, so it flipped down. And when we went to do our coordinates, the x stayed the same, but the y value became the negative value. So that's for reflections. Reflections are when it affects, you're changing the sign of either the x or the y. Compression is when you're multiplying either something to the x or the y. So when y is equal to f of kx, so we're multiplying something to the k value there, or to the x value, horizontal changes happen to y of f of x when x is replaced by kx. So if that k was greater than 1, we had a compression. And if you think back to when we did our graphs last year with the parabolas or the quadratic functions, if that value was greater than 1, our graph got narrower. So it was compressed or squeezed. And it was by a factor of 1 over k. If it was between 0 and 1, so a fraction, then there was an expansion. Our graph got wider. Same thing, it was by a factor of 1 over k, but because it was a fraction, then if it was, say, our k value was a third, so then that would be like saying 1 over 1/3, which is just 3. So if that, which would correspond to our a value that we used last year, made it wider. And then what happened to the x and y values, is this, whatever the factor was here, was multiplied to the x coordinate and the y stayed the same. So that was when we were doing things like this. This is the example for the when you have the a value, not the k value, but that's all that this part here means, is what happens to the coordinates. So if we take an ay, which is just the last examples we were doing, a vertical change happens when y is replaced by ay. So if that is greater than, and this actually should be an a value, but think of it as the a value instead of the k value. I'm not sure why. I think I just typoed there. So if a was greater than 1, we had that compression, a vertical compression. By a factor of 1 over a. So if it was a value of 3, then your graph, of course, got like our, oh, not this one, like on the other page, the first example. If it was, so it got wider. If it was a value of in between 0 and 1, so a fractional value, then it was an expansion, just like the last example we did. And what happened to the coordinate is the x stayed the same, but the y was multiplied by 1a, or the y was divided by whatever a value was. Okay, so now we have our little tools for doing reflections and compressions and expansions. So try to do them on some examples. So it says, given the graph of y is equal to fx, graph the function of y is equal to negative fx and y is equal to f of negative x. So we're going to do both of them, where we just put the negative sign out here, which is the same. This is the same as saying negative y is equal to f of x. They've already moved that over in the equation. So it says, show the mapping of key points. Well, let's just do a first. So for a then, if y is equal to negative fx, then that means, because this is the equation we're looking at, that negative sign is going to affect the y coordinates. So we're going from xy points to x negative y points. And if we're looking at y is equal to f minus x, then this is going to be going from xy coordinates to negative xy coordinates. Okay, so what we want to do is we want to pick some key points on that graph, on the graph that they've given us, y is equal to fx, and draw them. I need a black here. And draw those on there, identify them basically, and then we can do our mapping with them to show how they change. So I'm going to pick the point negative 3, negative 4, negative 1, 0, 0, 2, and then this one up here, which is 1, 4. So for the function y is equal to fx, I'm using the points negative 3, negative 4, negative 1, 0, 0, 2, and 1, 4. So for my graph, y is equal to the first one there, negative fx. So this one here, that means that I change the y values here. So then that means I multiply every single one of my y values by that negative sign, nothing happens to the x. So this stays negative 3, but this becomes 4. Negative 1 and 0, 0 and negative 2, and then 1 and negative 4. So if I go to graph these on here, my first point was at negative 3 and 4, so right there. Negative 1 and 0, 0 and negative 2, and then the last one was at 1 and negative 4. So this line now, try to make it straight. Ooh, that was bad. That's why you need to use a ruler. So that's what that one would look like, but straighter. Yeah, that's a little bit better. Okay, so then to do it for y is equal to f of negative x. So that means that the negative sign affects only the x value. So you always go back to your original function. So this becomes 3, negative 4, 1, 0, 0, 2, and negative 1, 4. So you plot those. 3 and negative 4 puts you down here. 1, 0, 0, 2, and then the last one was negative 1, 4. Use your ruler and join your dots. And there's your other graph. Okay, so this is the A part here to draw this. This is the B part showing the mapping of how I changed my coordinates. So you kind of have to do B before you can do the actual graphing. So it says, describe how the graph of y is equal to negative fx and y is equal to f of negative x are related to the graph of y is equal to fx, and then state any invariant points. Well, they're still both straight lines, and they would have the same slope. They would just be opposites. They'd have the y is equal to fx would be a positive slope, and y is equal to, with the negatives, is going to have negative slopes. Our invariant points are the points where the graphs have a point in common, or that point doesn't change when we do our negative values on there. So this would be the invariant point for that graph. So invariant point between these two would be at negative 1, 0. And the invariant point between these two would be at that 0, 2. Example 2, it says given the function fx is equal to x squared, so we know we're going to have a parabola. Transform the graph to sketch the graph of g of x. Describe your transformation, state any invariant points, and state the domain and range of the function. Okay, so for A, let's do that one over here. First thing that we're going to do is we're going to draw our function first, our basic function. So we're going to do fx is equal to x squared, which is the same as y is equal to x squared, which is just our parabola. So we do 0, 0, 1, 1, 2, and 4, and we won't get the 3 and the 9. So our parabola will look like this. Okay, so if we look at this, we have y is equal to, for this one, gx is equal to f of 4 times the function of x. So this is the same as saying y is equal to 4 f of x. So our a value here is equal to 4, so that means that our scale is 1 over a, so 1/4. Okay, so this 4, in our initial equation, what we would have, or the way it would have been written, this is like in solved form, we would have brought that 4 over here. So that was, sorry I lied here, this wouldn't be a scale of 1/4. Oops. If our a is equal to a 4 here and we bring it over, this is actually going to be, if I divide by 4 and divide by 4, it's going to be 1/4 y is equal to f of x. So that means a is equal to, 1/4. So if a is equal to 1/4, then that means to find your scale, it's going to be at 1 over a. So it'll be at 1 over 1/4, which is just 4. So that means you're going to take every single y value that you have and multiply it by 4. So that means it's going to be a vertical stretch, so that's our transformation. Of 4. So that means our original xy coordinates, which would be 0, 0, 1, 1, and 2, 4, that's all as far as I could plot on there, would change to x times, or xn 4y. So this becomes 0, 0 here, 1, 4, and 2 and 16, which I won't be able to draw on there. So let's do this one in blue. So I'm going 0, 0 is my starting point, so that's an invariant point. They've stayed the same for both of those. Excuse me. Then my next one that I plotted is that 1, 4. So be over 1, up 4, which puts me there. And then I can't do my 2, 16 because it's way off my graph. So this is y is equal to 4 f of x. So now to do b. Oh, we need to state the domain and range of this function. Sorry about that. I was just having a little choke. Now I'm okay. So our domain for this one, if we look, we could choose any x value that's on there. We just can't plot all the ones that are on there. So domain for this one, x is an element of real number. Our range, on the other hand, we never used a value less than 0. So y is going to be everything greater than or equal to 0. b, g of x is equal to 1/3 of f of x. Okay, so we can see from here I did the calculating, but I didn't need to do the calculating on this side because it turns out my scale factor is just that value, because that is our 1 over a is the flip. The a needs to be in front of there, but because we've moved it over already, so we know that our scale factor is just going to be whatever we're multiplying to that function of x. So therefore, our a, or scale factor, is 1/3. So that means because it's that fractional value, we can call it either a horizontal compression, where we're squeezing it down closer towards the horizon or the x-axis, or you could think of it as a vertical expansion where we're widening it away from the y-axis. So it's a horizontal compression or vertical expansion of 1/3 of that original function. So that means we're taking our x, y values and we're changing them so that x stays the same, but we're going to go 1/3 times y. So 0, 0, 1, 1, 2, 4. So if I do that over here, I have 0, 0, I have 1 and 1/3, I have 2 and 4/3. 3 and 9 I can put on here because when I do it here, it becomes 3 and 3. When I divide 9 by 3 or multiply 9 by 1/3, I have a value of 3. So I can plot that one on there. So 0, 0, there's my invariant point. 1 and 1/3, so it's just going to be just off of that x-axis. And 2 and 4/3, so that's the same as 1 and 1/3, so 2 over and 1 and 1/3 up. And then 3 and 3. So 1, 2, 3, 1, 2, 3. So my horizontal compression, I'm squeezing it horizontally, so it's getting closer to the y or x-axis here, so it's flattening out a bit. Or a vertical expansion because I am moving it further along that x or y-axis. Example 3. Given the function fx is equal to x squared, so our regular parabola, describe the transformation. State the invariant points and state the domain. So in these problems, or these examples, this 3, or the value, is being multiplied in there. That's a k value. So if it's being multiplied in here, it means we're going to have horizontal changes. Okay, so if the k value for a is equal to 3, then that means that my factor, my scale factor, is 1 over k, so it's 1/3. So horizontal changes means that it's going to affect the x coordinate. So that means we're going to have a horizontal compression of 1/3. So we're going from xy to 1/3 xy. So 0, 0, 1, 1, 2, 4, and we might as well do 3, 9 on here. Means that this is going to be 0, 0, invariant point because it didn't change. 1 and 1/3, 2 and 4/3, and 3 and 3. So if you look at this, this did the same thing. Multiplying inside the bracket was the same as having a excuse me, a fraction in front of your function. So it had the same thing, it just affected when you did it the other way, we did the transformation to the x value, or the y value, instead of the x. But this is going to give us the same graph. We do our, whoops, sorry, initial function, 1, 1, 2, 4, whoops, 2, 4, 1, 1, 2, 4, graph those, graph those. So then our f of 3x means that we're going to do our x, sorry, we're going to affect our x coordinate. So we're going 0, 0, oh, and I did the y coordinate when I wrote those down, that's why they're looking goofy. So this would be 1/3, 1, 2/3, and 4, and then 1 and 9, which we won't be able to draw on here. So 0, 0, then we go 1/3 and 1. Try that again. 1/3 and 1. 2/3 and 4. And then of course we can't do the 1 and 9 because it's way up here. But you can see it's made that skinny graph, which is the same as our skinny graph of 1/3 f of x. So b, g of x is equal to function of 1/4 x. So our k is equal to 1/4. So that means our scale is 1 over 1/4, which is 4. So because it's greater than, k is greater than 1, that means we have a horizontal expansion of 4. So we're going to change our functions from xy to 4xy. So we have 0, 0 goes to 0, 0. Again, that's the invariant point. 1, 1 becomes 4, 1. 2, 4 becomes 8, 4. And we can't go any higher than that on this one. Okay, so we draw our picture here, 0, 0, 4, 1. And I can't do 8, 4 because it's way off of there, so you can see it's going out like that. Okay, example 4 says, describe what happens to the function y is equal to x squared when you make each change to its equation and give the coordinates of the image of the point 10, 4 under each change. So this one is saying, if you went from your function to replacing the x value with a 5x. So you're going from f of x to f of 5x. So that means our k value is equal to 5. So the scale is going to be 1/5 because it's 1 over k. So your coordinate then, and this is going to affect the x coordinate. So it's going to go from an xy to a 1/5 x y. So 10, 4 will become 10 divided by 5 is 2, 2, 4. if we replace the y with a 1/3 y, so what they're saying in this one is we're going to have 1/3 y is equal to the function of x. So that's like saying y is equal to 3 f of x. So all I did was multiply both sides by 3 to get rid of it on the y. So then that means that you have a factor here of 3. So your xy coordinate is going to go to x 3y. So 10, 4 goes to 10, 12. Okay, example 5 says, describe what happens to the equation of a function if you make each change to its graph. So if you expand it horizontally, so horizontal means you're making changes to the x value. And if it says it's a factor of 2, then that means you have to do the opposite of that to put it back in. Because it was 1 over k was your value when you were solving it. So if it's 1 over k is equal to 2, then k is equal to find out what k equals, you would swap these. So your 2 would go down, your k would come up, so 1/2 is equal to k. So your general equation is y is equal to fkx. So then that means for this one, it'd be y is equal to f of 1/2 x. So if it's compressed vertically, vertical changes means that the y is affected by a factor of 1/4. So if the factor is 1/4, then that means that's what your a value was equal to. So that would have put that right in front of there, is 1/4 f of x. And if you want to write it in the proper form, then that means we have to move this 4 over. So to get rid of a 1 over 4, it's like dividing by 4. So we multiply both sides by 4 to get 4y is equal to f of x. So your a was equal to a 4. Okay, it says the graph of the function y is equal to fx has been transformed, write the equation of the transform graph gx. So it depends how you look at this. If you're looking at it, what happens to the x value. So if we're looking here, if this is our original graph, we went 0, 0, 2, 4 right here, then that means that in order to figure out what is it doing, it's moving away from our x axis. So then that means that we have to figure out what is the effect on the x. So if we look at the original graph on f of x, normally when we have f of x is equal to x squared, our coordinate is at 1, 1. But on this graph here, on the original graph of f of x, it's at 2, 2. Okay, so then that means we have to find out what was our k value. So if k is equal to 2, then we have to find out what was 1k equal to. 1 over k then would be, well, sorry, I did that wrong. I could just substitute that in. So 1 over k, our factor, is equal to 1/2. I should have wrote it like that. Okay, so we've factored it by a scale of 1/2. So because my points here doubled, then I know my k was equal to a 2, and if the k is equal to 2, then I have to find my scale, and the scale is always 1 over k, so it's a 1/2. So if we're going from y is equal to f of x, in order for that scale to be a 1/2 in here, then that means we just take a look at what was the k. So that means we went to y is equal to 2x squared. For the function of 2x squared, you could write it as y is equal to 2, bracket, x squared. So when I substitute in, I substitute my k value. I just need my scale factor as a description, but what I'm looking for is this k value, and the k value was 2. So if I look at vertically, so that's what happened horizontally, and depending on what the question says, you can do one or the other. I'm just going to show you what happened vertically. So vertically, if we're looking at this, what happened to the y values? So the original one, we already know that it's getting skinnier on us. So if it's getting skinnier on us, then that's kind of an indication. So vertical affects the y, and the x stays the same. So if we pick a point on here, it went from 1, 1 would be normal, and then if you pick a point on here, where right here is the point 1, 4. So it went to 1, 4. So that means then we had a factor of 4. So we went from here to here was a factor of 4. So if we substitute that into our equation, y is equal to, this is our original, it goes to y is equal to 4 f of x which then we can substitute. We know that f of x is equal to x squared, so this would be y is equal to 4x squared. And if we want to write it with the a value, remember this is our a value in the right spot, then we would actually bring it over to the other side. So if we divide by 4 and divide by 4, we have 1/4 y is equal to x squared. This is the way that I would leave it, as just a function like that, unless it says specifically to write it with your value with on the y. Okay, example 7. It says, given the graph of the function y is equal to fx, sketch the graph and identify 3 new coordinates when fx is reflected in the x-axis. So back to that little table on the second or third page, if it's reflected in the x-axis, then that means that we have to check, or we have to check, the y value is the coordinate that's affected. So that means we're going from xy to x, let me just fix that, x negative y. This should say B, this should say C, and this should say D. So graph A then, you pick your coordinates, and I said you just pick the points where your graph is changing direction. So A, B, or sorry, right there and right there, I'm naming them, but you don't need to. So we started at I keep doing the wrong one. -5, 0. negative 2, 3. Then our next one went down here to 2, negative 5. And then our last one is up at 4, 5. So if we are reflecting in the x-axis, that means we change the signs of the y value. So this stays negative 5, 0. That's an invariant point. Negative 2, negative 3, 2, and 5, and 4, and negative 5. So we plot those points. Negative 5, 0. Negative excuse me, negative 2 and 3. Sorry, negative 2, negative 3. 2 and 5. And then 4 and negative 5. So our graph is just a flip. Yep. Ooh, that one went way off. If it's reflected in the y-axis, then that means the x value is affected. So that means we go from xy to negative xy. So from our original one, which is right here, our fx graph, this becomes 5, 0, 2, 3, negative 2, negative 5, and negative 4, 5. So if we draw that on this graph, 5, 0, right there, 2, 3, negative 2, negative 5, and negative 4, and positive 5. So this time it's going like that. So if it's y is equal to f of 2x, so this is my k value. So that k value is 2. So that means my scale is 1 over k, or 1 over 2. So that means my x values are going to be affected by 1 over 2. Oh, I did purple. Green. So xy goes to 1/2 xy. So negative 5, 0 becomes negative 5 over 2, 0. Negative 2, 3 becomes negative 1, 3. So I'm just dividing by 2. 2, negative 5 becomes 1, negative 5. And 4 becomes 2, 5. Okay, so if I plot those, am I going to be able to see them? Yeah. Negative 5 halves, so that's the same as negative 2.5. So 1, 2.5, and 0. And then I go to negative 1 and positive 3. 1 and negative 5. Oh, I'm going to have to scoot that down a little. 1 and negative 5 brings us there. And then we're back up at 2 and 5. So you can see we've squeezed it together. That's that horizontal compression. And the last one, do orange. 2y is equal to f of x. So that 2 in front, that is our a value. So our scale is 1 over a, so it's a half. So this affects the y-axis. So a is equal to 2, so our scale is 1/2, or 1 over a. Oops. So our xy goes to x, oops, 1/2 y, because it's affecting the y value. So now I divide all of my y values by 2. So I started at negative 5, 0. That's going to stay negative 5, 0. Negative 2, 3 becomes negative 2, 3/2. 2, negative 5 becomes 2 and negative 5/2. And then the last one was 4, 5, so that becomes 4 and 5/2, or 2.5, right? So if we plot these, negative 5, 0, negative 2 and 3/2 are 1.5, so negative 2 and 1.5. 2 and negative 5/2, so that brings us over here, 2 and down 2.5. And then the last one was at 4 and 2.5. Oops, that's only 3. So if we were to look at this one, our domain stayed the same. We went between negative 5 and 4, just like we did in the other one, but our range changed. That, and in this one, sorry, in graph C, our range stayed the same, but our domain changed. Okay, last one. If the point 2, negative 3 is on the graph of the function y is equal to f of x, determine the new coordinates of the image point on the function y is equal to f of negative x. So if it's a negative x, that means it's inside the bracket here. This affects our x coordinates, so our 2, 3 becomes negative 2, negative 3. If it's y is equal to negative fx, this is then affecting the y value, so this becomes 2, 3. And that's it. The additional questions, you can work on those on your own, and then we can go over them. You can work on your assignment, which will be in your booklet, and do that for next class.